So in this video we're going to develop the formula that we need to use to calculate the area of a region that's been described with a polar equation. And the tool that we're going to use is the area of a sector formula that's developed in trigonometry. So what we want to remember that if we have a sector of a circle that's been swept out, we know how to calculate the area of an entire circle. The area of an entire circle is just pi times the square of the radius. But if we only have a sector or a fraction of a circle that has been swept out, what we need to do is multiply the area of a full circle times the fraction of the circle that's been swept out. And because 2 pi radians would be one full circle, if we've only swept through theta radians, then the fraction of a circle we've swept out is theta over 2 pi. And then the pi's cancel, and we wind up with this nice formula for the area of a circle that's 1/2 from the 2 right here, times the square of the radius times the angle that's been swept out. So this is going to be the big tool for finding areas of a polar region, for developing the formula. And the key here is to recognize that theta must be measured in radians for this formula to work. This is a radian specific way of identifying the area of a circle sector. So the problem is when we are working in with polar equations is typically we're going to be trying to find the area of some region where as we move, remember this is the polar axis right here, as we sweep through some angle theta, the radii will be changing as we sweep along. That's going to be the issue that we have to deal with. So what we want to do is say, hey, suppose I have 2 radial lines. Here's the first radial line. Here's the second radial line. So let's say this first radial line is located at theta naught. And then the last radial line, I'm going to say that it's located at theta sub n. And we'll see why I'm going to call it that here in a minute. So if we're interested in the area in this region, we're going to be interested in finding the area of this region as we sweep from theta naught through theta sub n. So we sweep through an angle of theta sub n here. We want the area between the 2 radial lines located at theta naught and theta sub n. And what we'll do to calculate that area is we'll break it into sectors and approximate the area. So for example, if I go right here, I establish a point, I sweep through some arc, and then from that arc I drive the radial line down to the origin. I could then pick up right here with another radial line, another arc, and then the radial line down to the origin, and another arc with the radial line down to the origin, and then another arc with the radial line down to the origin, and finally I could sweep through an arc with the radial line down to the origin. So what I'll do is we're going to break it into n sectors. So in this example I've broken it into 1, 2, 3, 4, 5 sectors. So this first angle is going to be the start angle. So remember, polar coordinates, our coordinates are theta. So this point right here would be r naught, the radius r naught, comma, theta naught. And we'd sweep all the way through till we got here. And at this point here would be described by the nth radius and then theta sub n. In the case where I have 1, 2, 3, 4, 5 sectors, I would actually put r sub 5, theta sub 5. This would be r naught, theta naught, r1, theta 1, r2, theta 2, r3, theta 3, r4, theta 4, r5, theta 5. But in general, we're just going to say n sectors. We're not going to restrict ourselves to 5. So this would be the nth radius, the nth angle. So when we sweep through from theta naught to theta sub n, when we sweep through this angle, the angle we've swept through is theta sub n minus theta naught. And then if we've broken it into n circle sectors, the angular width of each circle sector is going to be the total angle divided by n, the number of sectors you've broken it into. And that's going to be this little guy here, and we're going to say this is delta theta. That's the change in the angle as you move through each sector. So this, the last angle minus the first angle divided by the number of circle sectors is going to equal delta theta. And then what we're going to want to do is add these all up. So if we think about the ith, if we think just about the ith sector, right here, the radius is going to be r sub I, and the angle position is going to be theta sub I, r sub I, theta sub I. So how would we find the area of that ith approximating sector? So the ith sector, we would calculate its area as the ith approximating sector. Its area would be 1/2 r squared, so that would be r sub I squared, and then it'd be times the angle, but the angle is the same for each sector. The angle for each sector is just delta theta, so we'd multiply by delta theta. So if we were trying to approximate the entire area between the curve and the origin as we sweep from the first radial line through to the last radial line, we would need to add these all up, and then we'd say, hey, we can approximate the area of that circle by adding up, taking the sum from I equal 1, the first sector, all the way through the nth sector, add up all those areas, and it will approximate the area that we're interested in. And then this is where calculus kicks in, because we don't want an approximate area, we want the exact area. And the way that we do that is we let delta theta go to 0. The way that we make delta theta go to 0 is, instead of cutting, we take the limit, as n goes to infinity. We cut it into infinitely many sectors. And so we take the limit on this. We take the limit on this as n goes to infinity. We'll cut this region we're interested in into infinitely many sectors. And when we do that, what's going to happen, is that this ratio right here is going to go to 0. Theta sub n minus theta naught divided by n. The limit as n goes to infinity is going to be 0. So if delta theta is going to 0, the convention in calculus is to rename delta theta to indicate that it's going to 0. So instead of calling it delta theta, we call it d theta, saying, hey, we're taking the limit as the number of approximating sectors goes to infinity, which is making this ratio here become infinitely small or go to 0. Let's call it d theta. So to get the exact area under the curve, the area equals, we take the limit on this summation as we let the number of approximating sectors go to infinity. When we do that, we get the exact area, and then we rewrite things using our calculus conventions. We say, hey, this is sigma, or sum. In calculus, when we take that limit as delta theta goes to 0, now we say the sum. We use a different symbol for the sum, but it's still taking a sum. We recognize that 1/2, a constant, can be factored out front of a summation. So we factor that 1/2 out front of the summation. Now as delta theta goes to 0, we run through all possible radii that can happen. And instead of calling it delta theta, we call it d theta, because it's infinite. It's close to 0. It's infinitely small angles at this point. And then we run from theta naught through theta sub n. We take all of these calculations as we run from the first angle through to the last angle. And then in polar coordinates, polar equations, the radius is changing as a function of theta. So from the last video, we know that the radius is going to be some function of theta. So we could also replace the r squared here with f of theta. That was our issue, is that the radii were changing as we swept along this curve. So that's how you calculate the area between the two radial lines, the start radial line and the end radial line. This calculation gives us the area between those two lines. So the next slide, all he did is type up that derivation nicely. So this will give you something, if you pause the video, you could put something nice and clean in your notes, and it has some of those details that are important to pay attention to. So you want to read through this carefully and get it into your notes. In the next video, we'll show some applications of this formula.